Sergey, other last.
Okay. Okay, so it is visible to you?
Yes.
Yes, sir.
So we were discussing about registers, and just to continue the discussion, we will start with universal shift registers. So, bache, what is actually this universal shift register is, and what are the functionality that this register may provide, right? So sometime what happened actually when you are trying to access the output of a shift register, so the information entered serially by shifting can be taken out in parallelly, right? And if parallel load capability is added to a shift register, then whatever data you entered in parallel that can be taken out serial fashion by shifting that data into the register. So some registers provide this facility, and this is actually necessary input output terminals for parallel transfer. Fine. So they may have both shift right and shift left capability. So they may used for both left to right or right to left. Fine. So here you actually can see this is serial input for when you want to use this register as a shift right register, and this is the input when you want to use this register as a shift left register. Fine. So and that's why it is called universal shift register. According to your need, according to your choice, you actually use this register in both ways, shift right or shift left. So that's why it is not left shift register or right shift register. It is only shift register, universal shift register. So what are the capabilities that a general shift registers may have, and these are the capabilities. So a clear control to clear register to the 0 means you can set reset kind of things, and a clock which input to synchronize the operation, a shift control to take enable shift right operation, and serial input and output line associated with that shift right, and shift left control to enable shift left operation and the serial input lines associated with this shift left, and parallel load control to enable parallel transfer, and an input line associated with the this parallel transfer. It must have n parallel output lines, and a control state that leaves information in the register, and register in change in response to the clock, and other shift registers may have only some of preceding function with at least one shift operation. Fine. So when you talk about you can see unidirectional shift registers, so or any other register, so they may have only one shift operation, whether it is right shift or it is left shift. But the bidirectional, if register is bidirectional, generally it is called, it is referred as universal shift register. Right. So so now if we discuss this diagram, so here this consists how many flip-flops are there and which kind of flip-flop we have used?
4D flip-flops.
4D flip-flops. So this consists 4D flip-flop, right? 1, 2, 3, 4. So and we have 4 multiplexer, and these 4 multiplexer actually have 2 common input. You have 2 common input, S1 and S2. So input 0 in each multiplexer will selected when S1 and S2 0. So if you want to select this 0, so both should be 0, and when input is when you have to select input 1, so your S1 S2 value will be sorry, S1 S0 value will be 1 0, sorry 0 1. So it leads 1, and similarly others. So when actually S1 and S2 is 0, so present state of this this register is applied to the D flip-flop, and this condition forms the path of output, and the next clock will actually catch the triggered, and where the clock is, you have a common clock here. Fine. So so you can see the mode control from here when S1 and S2 is 0, or the 0 input is selected, so there is no change. 0 1 it is left shift, sorry right shift, and when 1 0 it is left shift, and 1 1 it is parallel load. Fine. And you can simply see from here as well, this 1 is for right shift. So the input, so if you want to generate this one, so input should be 0 1, and here for left it is 0, so binary of 0 is 1 0, and similarly the same thing is replicated here. So in order to perform shift right, the input should be the mode control should be 0 1 and 1 0 for the left shift, and if it is 1 1, so it will perform the parallel load function. All right, so this complete our shift registers. Then after shift registers, we have the counters, ripple counters. So just to move on board side, and we will discuss something, then we will come here again. So we have counters. So what is counter? You know that counter is a register which actually goes through a prescribed sequence of state, and these prescribed sequence is nothing but depends upon the application. Whatever the application or the input pulses you are giving, so that pattern may be decided from that. So if we note it down, so a register that goes through a prescribed sequence of a state. Is called counter. Fine. So if you have a n bit counter, if you have a n bit binary counter, if you have a n bit binary counter, so tell me from where to where it can count. So it can count 0 to, if you have an n bit count, 0 to
n minus 1.
n minus 1. Is it? No. Anyone else? 0 to?
So 2 raised to power n minus 1.
2 raised to power n minus 1. Exactly, Vijay. N bit. So how many combination you can create? 2 ki power n. So let's say n is 4. So 2 ki power 4 is 16. So what is the maximum decimal number which can be generated with 4 bit is
15.
15, right? So if you have a n bit counter, so you can count 0 to 2 ki power n minus 1, 2 ki power n minus 1, right? and to create n bit counter, how many flip flops will be required? To create a n bit counter, how many flip flops will be required?
And
N number.
N number of flip flop will be required. Fine. So now we have two available categories of counter. We have two available categories of counters, and these are ripple counter and synchronous counter. Counters. One, ripple counter. Second, synchronous counter. Right. So what is difference between these two counters, a ripple counter and a yes, anyone is saying anything, Beta? Any doubt, any issue? No. Okay. So the basic difference between this ripple counter and synchronous counter is a ripple counter, the output of a flip-flop transition serve as a source and triggers from other flip-flop, or you can say some or all input are triggered by not by a common clock. The input are triggered with different clocks. Fine. And in synchronous counter, the input of all flip-flops receive the same clock. Input are triggered with the help of same clock in case of synchronous counter. So you can write here different clocks, and here all inputs are triggered with common clock. Right? So this is the basic difference between ripple counter and synchronous counter, and rest of the things we will see when we will discuss these one by one. So I'll start with first binary ripple counter. So, ripple counter. So again, just to recap kind of things, a register that goes through a prescribed sequence of states upon the application of input pulses is called counter, and the sequence of state may follow the binary number sequence or any other sequence of states. So it is not necessary that each counter follow the binary number sequence. No, and it may follow any sequence of the states, and these sequences are exactly application dependent, what kind of application you actually want to create, right? So a counter that follow the binary number sequence is called a binary counter. An n-bit binary counter consists n flip-flop and can count binary number from 0 to 2 to the power n minus 1. Right, so n-bit binary counters consist n flip-flop and can count from 0 to 2 to the power n minus 1. We have two available categories of counters. One is ripple counter, another is synchronous counter. In ripple counter, the flip-flop transitions serve as a source of trigger of other flip-flop, and you can say that C input, that is counter input of some or all flip-flop, are triggered not by common clock, rather by the transition that occur in other flip-flops output. We will see it how actually it is happening. And in a synchronous counter, counter input of all flip-flop receive the same or common clock. Fine. So first is the ripple binary counter. So in ripple binary counter, it consists a series of connection complementing with flip-flop, and output of each flip-flop connected to the C input of next higher order flip-flop. So they see here. So this is the input counter. This is the clock. Fine. And this clock is not common actually. You can see here, clock is this. Now the output of this state, output of this is actually working as a clock of second flip-flop. Similarly, the third flip-flop, the clock of third flip-flop is nothing but output of the second one. So here simple phenomena, whatever we are saying, that here we didn't have the common clock for all. Fine, each and every flip-flop have a different clock. Right? So flip-flop holding at least significant bit receive the incoming input counting pulse, and a complementing flip-flop can be obtained from a JK flip-flop with J and K inputs tied together, or a common or a D or T flip-flop. And third possibility to use a D flip-flop to complement the output connected to this particular input. And this in this way you can actually have this D input is always the complement of present state. Right. So this is here you can see the binary count sequence. This is your binary count. ये कहां तक जाएगा आपके पास? ये 0 से शुरू होगा और ये कहां तक जाएगा? 9 तक, and then 0 to 9, and then this. Fine. BCD Ripple Counter. So BC in here, the decimal counter follows this sequence of 10 state and return to 0 after the count of 9. Such counter must have at least 4 flip-flop to represent each decimal digit, and it is simple phenomena because decimal digit represented by binary code is required at least 4 digits. So sequence of state in the decimal counter is dictated by the binary code to, and that code exactly represents that particular decimal digit. A decimal counter, similarly to a binary counter, except that the state after 1001 code decimal right is 0000. So here 0000 means 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then after 0. So this is binary BCD Ripple counter with the help of JK flip-flop. Here you can see that 4 outputs are designated by the letter this Q, Q1, Q2, Q2, Q4, and this Q8, and it is what is this numeric subscript is actually depicting here. Q1, Q2, Q4, Q8 is the binary weight of corresponding bit in BCD code. In BCD code. So Q is applied to the C input of both Q2 and Q8, and Q2 is applied to the C input of Q4. So Ripple counter is again a synchronous sequential circuit. Signals that affect the flip-flop transition depend upon the way how it changes from 1 to 0, right? And again the operation these conditions are derived from the logic diagram and from the knowledge how JK flip-flop operates. And now you must remember that when C input goes from 1 to 0, the flip-flop is set if J is 1 and it is cleared if K is 1, and it is complemented when J and K both are 1, and it left unchanged if J and K equals to 0. So it is again the the operation of JK flip-flop kind of things. Next thing is synchronous counter. So in synchronous counter, as we have already talked a bit, that synchronous counter are different from the Ripple counters, right? And the thing which is change here from Ripple counters is that clock pulse are applied to the input of flip-flop, and it is a common clock which triggered all flip-flops simultaneously. You can see here that here all flip-flops are not triggered simultaneously. All flip-flops are not triggered simultaneously, whether it is any kind of a Ripple counter, because we have a different clock to each of the flip-flop. Here, a common clock triggers all flip-flops simultaneously, rather one at a time succession, as in a Ripple counter. Fine. So in synchronous, we have a common clock which triggers all flip-flops simultaneously. So now the decision whether a flip-flop is to be complemented is determined from the value of the data input, such as T or JK or J and K at the time of edge clock. So if T is equal to 0 or J and K, J equals to K and it is equals to 0, so it is not change its states. And if T is 1 and J and K is also 1, so flip-flop complements. So the synchronous counter can be triggered with either with the positive or negative edge clock. Binary counter. So 4-bit synchronous binary counter. Fine. 4-bit synchronous binary counter. Right. So in this synchronous binary counter, flip-flop at least significant bit is complemented with each pulse, and a flip-flop in any position can be complemented when all bits in the lower significance positions are equals to 1. And synchronous binary counters have a regular pattern and can be constructed with complementing flip-flop and gates. right? And complementing of flip-flops in a binary counter can be either GK type or T type or D type with XOR gates. So here you can see that if the present state of counter is this A3, A2, A1, and A0. See A3, A2, A1, and A0 is 0, 0, 1, 1. The next state will be 0, 1, 0, 0. The counter is up-down binary counter. So in synchronous countdown binary counter, it goes through a binary state in reverse order from 1112 down and to 0000 and to back 111 to repeat the count. So it is possible to design a countdown counter in the usual manner, but result is predictable by the inspection of downward binary count. So bit in the least significant position is actually complemented with its pulse, and the bit in any other position is complemented if all lower significant bits are equals to 0. Right? So LSB here always complemented, and the second significant bit is complemented because first bit is 0. The third significant bit is complemented because first two bits are equals to 0, but fourth bit does not change because it will not all lower significant bits can be equals to 0. Fine. So you can say that a countdown binary counter can be constructed here as shown in this particular figure, right? And except that input of AND gates must come from the complemented output instead of the normal output of previous flip-flop, right? And two operations can be combined in one circuit to form a counter capable of counting either up or down. So up or down, and sorry, and you can see here that this is designed with the help of this T flip-flop, and this when up input is 1, the circuit counts up since the T input received the signal from the various previous normal output of the flip-flop, and with the down input is 1, the up input is 0, the circuit counts actually down, and since the complemented output of the previous flip-flop is applied to the T input of this flip-flop, right? Final counter is the BCD counter. So in BCD counter, it's binary coded decimal from 0 to 9 and back to 0. So a BCD counter actually counts this BCD coded decimal again 0 to 9 and back to 0. So because you are returning to 0 after counting 9, so BCD counter does not have a regular pattern, right? So unlike a straight binary counter, to drive the circuit of BCD synchronous counter, it is actually necessary to go through the sequential circuit design procedure. And what sequential circuit design procedure was? We have to go through map and all those things. Fine. So state table of BCD counter is this: present state, next state, and output. Fine. So input of the T flip-flops are obtained from the present state and next state condition, and also shown in the table where output Y, which is equals to 1 when all states is 1, 0, 0, 1. In this way, Y can enable count to the next higher significant decade, where the same input pulse actually decade from the 1, 1, 0, 0 to 0, 0, 0. Right. So so you can find out TQ1, TQ2, and TQ8 and Y as well. So how you will again, how you will actually find it? कैसे आप निकालोगे इनको? How you will get this TQ1? It is 1. Why? कैसे निकालोगे भाई? Am I audible?
Yes, sir.
Okay. So how you will calculate it, Bache? So just recall a simple line when what I told you. The drive of the circuit of BCD synchronous counter must go through the sequential circuit design procedure. And what that procedure was, कैसे करते थे उन circuits को design? How we design those circuits? With the help of K-map. So here 4 input, 4x4 map, Q1, Q2, and Q4, Q8. इसके लिए जा रहे हैं तो ये 1 कब है? ये हर कंडीशन में 1 है, 1 1 1 1 1 सब जगह आ जाएगा. सो सबका एक 16 के 16 आ गए. फिर क्या कॉमन आएगा?
पूरा ग्रिड का.
पूरा ग्रिड कॉमन है. अब इस पूरे ग्रिड में क्या कॉमन है? कोई वेरिएबल तो कॉमन रहा नहीं.
1.
Yes.
1 common. Similarly, TQ2, TQ4, TQ8, and all other output. Y. Fine?
Yes, sir.
BCD counter with parallel load. So counters may employed in digital system quite often requires a parallel load capability as well for the transferring the initial binary number into the counter prior to the count operation, and when it is equals to 1, input load control is disabled and operations causes a transfer of data from 4 input to the 4 flip-flop, and if the control of inputs is 0, clock pulse do not change the state of the register. So this is 4-bit input, 4-bit binary counter with help of parallel load. So this completes your counters. Next we have error detection and correction and Hamming codes. Fine. So you might remember that we have already discussed some error code that was parity bit. Fine? Remember or forgot?
Yes, sir.
Yes, sir.
So इस टॉपिक को बच्चे कल शुरू करेंगे. Error detection and correction. So उसमें हमने क्या करा था? In that case we have seen that how you can think of that whether this is an error or not. But in that case you cannot tell in what bit actually error is. And with the help of parity, if you remember, we cannot detect if there is an error in more than 1 bit. Fine. So here we will see how we can actually detect and correct the error. किस bit में error है and what will be the correct bit for this, right? See it in next class. So I'm stopping here.